Okay, let's get started. So for this session, I want to kind of fully look under the hood and actually look at the code that we've been running so far, one of these simulation models, and then also show you how you can then tweak that code to make it do things that are not sort of already hard-coded in it. So we'll do some coding. We will again have an R script open, but I want to start again by loading and going into the menu just real quick, so you can see where we can pull down the code. So here's a menu coming up, and then here you have this convenient download R code for all simulations. So I'm going to do that now. And I'm going to stick it into the SISMID folder. And basically what you'll end up is with a zip file. And inside the zip file, all of the simulations that you can get through the graphical interface are there. And so you can open each one. The one we want to look at now is the bacteria one. So it kind of matches a bit what we discussed about. And it's the one that's called extended bacteria. So I'm going to take that and just copy it into this folder. So if you want to work along, just copy it somewhere. And then if you have RStudio set up, when you click on it, it should open in your RStudio session. So that's the one we'll be playing with. So first, when you open it, you actually see a lot of text. Remember the green stuff that starts with the hash is text. And really everything here at the top is just the part that when you call the help file, and I'm going to go out of the app again. So I have my console back. So basically I just shut down the graphical interface. Remember we looked at yesterday that when you call the help file for these ones, in this case, the extended bacteria, it gives you all this kind of stuff here. And you can see that this text here, description, is this block. So the way that is done when someone makes an R package like this one for the functions, you basically document it inside the function. Now, when you write your own code, most of the time you don't write code that you will put out as an R package. You might share it with collaborators, but not as a formal R package. So you don't actually need all this stuff here. I mean, you can if you want to be very formal, but otherwise, you can just have regular comments in there. So all this stuff here, these param means down there, all of these, what's then later called arguments, what you put into the function, and then the details and the values. So all of that is not fully needed. So what I'm going to do now, I'm just actually going to delete it all. And the reason why I do this is so you see what's actually just the code that runs the model and is not part of the sort of explanation and tutorial. So this is it. This is the whole simulation that runs underneath. And so you see the top here, it's written as a function where you give it the starting conditions and the parameter values. And here's the name of the function. And then everything inside of these curly brackets is basically the specification of the function. And in this case, and for most of all these apps, I'm using a package called DSAIRM that runs differential equation models. So I don't actually have to write that myself. All I have to do is specify the model in a notation that kind of looks similar to the math notation. And this is all done in this block here. So DSAIRM asks you to basically write a code block that sort of looks like the differential equations. And really what you have is this dB means sort of the dot notation. Remember dB by dt, which we abbreviate with the dot. And then on the other side, you put all these flows on there. So in this case, actually, I do want to go real quick back to it so we can look at the model. So in this case, we have a model with bacteria and then an innate and an adaptive response. Here's a diagram. This needs to be called innate response, not immune response. But so bacteria, innate response, adaptive response. And so you have these different processes. So bacteria grow. Now before we had viruses, so they were inside cells. In this case, we assume sort of extracellular bacteria, so they just sort of grow on their own. They don't need to be inside cells. So, this model would not apply to TB, but it could apply to the other two pathogens Paul just went over. So we have bacteria that grow at some rate, GB, and when it reaches Bmax, it sort of slows down. They can die at some rate, and then they can be removed or killed by both the innate response at that rate Ki and the adaptive response at that rate Ka. And then the immune response here is induced by the bacteria. And the way I've done it here now is that, initially the induction is sort of proportional to the bacteria. And then when the innate response reaches some maximum level, then it basically levels off. So the idea is, it gets induced. The more bacteria there is, the more the immune response gets induced, but it can't get induced forever. At some point, it kind of levels off once it reaches whatever sort of the biological max could be. And then it decays here at some rate. And then the innate response in this model again activates the adaptive response. And you see something slightly different here than we've seen before. Here I'm actually assuming the induction of the adaptive response scales with the logarithm of I. Quite often in biological systems, you see sort of a log dependence on certain quantities instead of sort of on an absolute scale. So that is quite often a reasonable assumption. Now, in this case, again, since these are toy models, example models, I could do either way. I just decided to do it this way here. When you have your real system, you have to decide what you think is the most realistic or reasonable way to do it. And again, quite often there's probably more than one way that is justified. And then you either have to pick one or you can explore multiple versions of your model and see how results might or might not change. So this is a diagram, and here are the three equations. And so basically these equations here is what we're now needing to put into code. And you see here is the changes of each of these variables and then the processes that can happen. And so if you look here, it's pretty much exactly the same thing, just now written in code. So the translation from the model to the code is actually not that hard. It's almost, one-to-one. Now, if you have a model where you decide to use Greek letters for the parameters, which a lot of people like doing, I try to not use them here to just make it a little bit easier for newbies to follow along. But you often see that someone might call this a beta or so, then you either have to, in your code, write out the word beta or just call it B or something. But other than that, there's often a very easy translation. So this is here, we're specifying the equations, and then the DSAIRM package just requires that we return it as a list in that order. So that is sort of another function inside the main function that specifies the model. And then this here is the main model. So remember here, these are all the inputs that we're feeding into the model. And so here we're just grouping them together. We make a vector for all the times, which is the start time, the end time, and the time step. We make a vector for all the variables, the starting values for each of them, and then all the parameters. And then we just feed that into this function ODE that comes from the DSAIRM package. We tell it what the y values is, that's ODE's notation of variables, the parameters, the time, and then we need to tell it the function. And these last two things are just some settings that tell the underlying function how exactly it should run. For our purpose right now, not that important. So that's it. So this one function call produces the result, and then we just, because the whole package wants it in a certain structure, we turn it here into a list so it shows up the way you remember. So we can now, of course, run this thing, which is going to go here into the R console. And we could run it with its default values. Let me call it res again. So it ran again. And, if we look at the res, you get this, what by now is maybe a little bit familiar, this data frame, where it's basically 4 columns. First column is time, and then every other column is the variables in the model. So in this case, we have 3 variables, the bacteria, the innate, and the adaptive response. And then every row is that variable at a certain time. So we could, again, do the plotting of this. So that's the bacteria plotted as a function of time. You know, they grow and then they settle down somewhere. And we could do that for I. Huh? Looks exactly the same. No, it doesn't. I guess it follows the same pattern, but the numbers are different. And let's see what A does. Yeah. So it seems like the settings, the default settings are such that the adaptive response doesn't do much. I just ran it with the default settings, so I didn't try to do anything. Now, of course, we have the options that we discussed yesterday. You could go through it with the tasks of the graphical interface. So actually, in this case, I haven't actually fully written the tasks yet because this is an app that we put in just this year. And I didn't get around to writing all the tasks because I knew I wasn't going to need them for this. But, you know, almost all the other ones have the tasks, so you could do that. You can do it like we did yesterday. You could, what I just started doing here, sort of call the code and run it. But now what we want to do is we want to go one step further. As I mentioned yesterday, the disadvantage of doing the approaches we covered yesterday is that you have to use this model, and that's the model. And you can use any of the models that come with the package, but if you want a slightly different model, then you need to adjust the code. And that's what I want to show you today, how you could use this kind of code as a starting point and adjust it to something that, you know, might be closer to what you would want to address. And so for that purpose, first, I'm going to set a separate script here. And so in this script, I will actually then, you know, call the other code that I will write. So, you know, since this is now our own one, I have to always source what that source does. It kind of executes that R script and makes things that's in the R script available without running it. So it's sort of the equivalent when you call the library command to load a whole package, everything in that package becomes available to you. If you just want one function, you can make it available like this. And so I'm going to just put my new script in the same folder. I'm just going to call it script 1. Okay, let's see if, we need to make sure we're in the right folder. So now we are in this folder here. So, and this function that simulate needs to be in the same folder. So I sourced it, so now I can call it here. Just copy this code here. And, now we can. Now we have res available. Okay, that's just a setup. So, but what we want to do now is we now want to say, okay, let's change this one to something of interest. And so I want to try to sort of get at something that one of you, Nancy, posted and asked a question about in Slack and also earlier during the discussion, which is, how can you model genetic diversity? Now, in general, if you want to do that fully, you might have, instead of just one compartment for bacteria, you might now have a whole bunch of compartments for the bacteria, each one representing a different genotype. Wait, there's a question. What's the benefit of using the source? Well, the nice thing is if you split it like this, I could now have 5 different scripts here that all do different things, but they all run this underlying code here. If I didn't do that, I would have to copy this code into each one of my 5 different scripts. And remember from yesterday that principle of dry, don't repeat yourself. So if you need a piece of code more than once, you kind of want to put it separate, and then you just want to pull it in when you need it. So that is kind of the advantage of this way of doing it, that I could now run 5 different scripts. Each one uses this to explore it. So that's the advantage of that. So back to that idea of diversity here, if we wanted to sort of model that fully, we might say, okay, we think there might be 100 genotypes. So instead of just having one compartment for the bacteria, we could now have B1, B2, B3, and so on, like 100 different B variables, and each one represents a different genotype. You can do that. But of course, the model gets big. And so what you often see what people do when they want to explore that kind of thing, what they're actually doing is they start with two. And one of them they consider kind of the wild type, and one of that they consider sort of the mutant. It could be either just a single mutant, the one that comes up first, or it could be the collection of all the mutants. Where you see people do these kind of models, for instance, is for drugs. There might be the wild type that is sensitive to the drug, and then the mutant that is resistant to the drug. So that's sort of a first step. It doesn't get you at all the diversity, but you can start, building some intuition. What would happen if you had two strains in this case and they behaved slightly differently? And so I figured we could try that now. We built a little model. We extend this model by adding a second strain in there. Then we have to decide what's different about the strain, and then we can explore our model, see what happens. So that's what I want to do now. So basically what I'll be doing, and if you want, code along here, I'm copying this equation here. And I'm just now labeling them 1 and 2. And, of course, I have to in there everywhere labels. And so now here's the first decision, right? We have this B max, which is kind of the, carrying capacity, or how high can these numbers grow. Now I have to decide, do these two mutants have different values there? Are they, whatever their genetic difference is, does it make them phenotypically different such that one can grow to higher levels or not? Or do I assume for what I'm trying to do that, no, they don't differ in that aspect? For now, I think I'll just say that we assume that this B max is the same for them, that they don't differ in that. What I will let them differ is in the way they interact with the immune response. So we assume the B max is the same. Of course, you can always, sort of double every parameter and then later set B max 1 equals B max 2. That gives you the most flexibility if initially you make them all separate, and then you can choose to make them the same by just giving the same value. Now for simplicity, so we don't have to drag that much code around, I just say, okay, now the B maxes are the same. The same here, the dB, that's the rate at which these bacteria die. Again, I'm making the assumption here that there's no difference between these two genotypes in that rate they die. So I'm not labeling those rates here 1 and 2. Of course, the actual bacteria I have to label 1 and 2. Line 1 and 2 here too. Okay, now we're coming to these different parameters that have to do with the immune response. So this is killing by the innate, Ki, and killing by the adaptive. And so now I could make them different between the two. Honestly, I don't know yet where I'm going with this and what exactly we're going to do. So why don't, for now, I'll just say they might be different. And so I'm doing this too. So basically that could now kind of represent the one mutant is kind of a bit of an immune escape mutant, right? Maybe if Ki2 and Ka2 are lower than Ki1 and Ki2, Ki1 and Ka1, it means that the number 2 mutant is less quickly killed by the immune response. It has acquired something that, makes it somewhat more protective. So these are the bacteria equations. Now I need to go in here too, because now I had B, now I have to change this. I'm assuming here that the innate response is growing proportional to the number of bacteria. Well, initially I just had B. Now I have to decide, are they growing proportional to the number of B1 or B2 or the sum of the two? Or does each one have a different impact? It could be that for some reason B2 is less immunogenic, so it doesn't sort of induce or tickle the innate response quite as much. So let's say for starting simple here, I'm just going to do the sum of the two. So that's sort of the total number of bacteria, no matter which genotype, that's by how much the innate response is induced. I could, if I wanted to change that, I could put some, A1 or A2 in front of here. And if I set them to different values, that would basically change the contribution of each of those two. So I could say, okay, B1 or B2 is more immunogenic, induces the immune response more. I'm going to leave it out for now. We can decide later to maybe stick it in. Okay, and now we're coming here to the adaptive response. Again, you know, actually here in the adaptive, we don't have a problem because B is not in there. The adaptive response just grows proportional to I and the case by itself, so we can leave it alone. So now we've changed the model a little bit. We might go ahead and change it a little bit later, but let's try to get this model going here. So now, of course, I need to go into the various places and update things. So instead of just having B up here, I now need B1 and B2. And B2. I can start them for now with the same. So we decided G and B max and DB was not different between them, but those were different. So we're making 1s and 2s out of those. And you can already see what I've mentioned before. You know, with every additional detail you put into a model, your model gets bigger, you have more parameters, and you need to have values for those. And of course, that's often the limiting factor, that at some point you have too much to put in there. Now we need to do it down there too. So everywhere where you see this, need to adjust it to the 2s. And then same here. Okay, I think that is everything. We can see if that works. I'm not just gonna in case we build a few more, I'm just now going to call this one here version 1. You do not have to name the function inside of R script the same. And in fact, you can stick more than one function into an R script. Personally, I like to have the name of the file to be the name of the function inside the file, and also to always just have one function in each file. It just helps me keep things straight, but that's not a requirement. You can have, in fact, we have this function here inside as well, but that's not sort of the main function. So, then we would want to call version 1, and let's see, fingers crossed, let's see if that works. The source doesn't tell us yet because it just makes it available, but now if we run it, we'll see if we get an error message or not. Okay, something didn't work. Okay, and that's one of the joys of writing code and being a newbie. You get a lot of error message and usually weird ones. Here this is like, what exactly does it mean? Especially when you're new to it, it's not quite clear. Now, I've done it many times and I've seen this error message often enough that I know exactly what's wrong. Here, down there, when I return it, I forgot to do that. I did forgot to adjust it there. Okay, let's see if that was the only mistake. Let's try to run again. Okay, it looks like something worked now. Let's look at it. Okay, now you can see we have B1, B2, I, and A. So we have all 4. So we can I'm actually going to pull the package in just so I have the generate ggplot function. So I can just use the plotting thing. And remember, I have to turn this thing into another list. So here I get it plotted. Now, what you see, our question, what did I change to fix the error? Okay, I had down there, this is the last statement in this block that returns all these back. And I forgot to make it, to change the DB to DB1 and DB2. I need to return all 4 here, every variable. So that was the mistake I had, and that I just fixed now. So that was the complaint, because it checks if I have 4 variables here, then expects that 4 variables are returned here. And that's what the complaint was here. The derivatives returned 3, because I forgot to do that here, must equal the length of initial conditions, which is these 4. So that's what the error meant.
Just a quick question.
Mm-hmm.
The generate ggplot is a function from the DSAIRM package?
Mm-hmm. Yes.
Oh, cool.
Yes. We wouldn't need that here, right? We could do our own plotting if we wanted to. That's just me being a little bit lazy right now. In general, you probably would not want to do it. You would probably want to convert that outcome somewhat and then just use general ggplot because you have more flexibility. So, you know, this is just for demonstration right now. So because it's quick and we get a reasonable enough plot, but you would probably, for any research, you would probably just want to take what you get out of this res thing, which is the return from that simulation, and process it to make exactly the kind of figure you want to make.
So that function is so useful. We can use anywhere for so multiple things. That's cool.
You could, yes, but you will soon reach the limits of it, right?
Yeah.
If you want to, for instance, label this up there differently, or you want to have different colors or so, you can't do that easily. I mean, you can do somewhat. If you look at the help file for it, it will tell you, things you can do, and it tells you can set, legend and line size. So it lets you set some things, but you can try how far you get with it, but it's really kind of meant as a helper function for this specific package, and it doesn't give you quite the full flexibility you would get from if you just use straight ggplot. And that's always a general trade-off, right? There's so many nice tools in R, and if they do what you want them to do, then often you can use them. Sometimes they might not give you what you want to do, and then you might just have to write a few extra lines of code yourself. You have more flexibility at the trade-off of more coding. That's a very general thing. The more flexible, the more coding, and then the more convenient, the less flexible. That's always a trade-off. So what we're seeing right now is that our two bacteria are on top of each other, and I hope this is not surprising to you, because we decided that the only thing where they might differ is in the rate that they are killed by the two, the innate and the adaptive response. But right now we chose those values to be exactly the same. So of course, everything's the same between those two strains right now. So nothing exciting happens yet. So let's now, change that. And so instead of setting the defaults here different, I'm going to leave the defaults as they are. But when you call these functions, if you don't provide anything, it uses the defaults that are given here. But you can override those defaults. So I'm going to now do, and you don't have to specify each one. You can just specify the ones that you want to be different than the default. So I'm just now going to say that, actually, wait, we might want to say this is less detected by the immune response. So now the killing of number 2 by the innate or the adaptive is lower. Instead of 10 to the -4, I made it 10 to the -5. So what we should expect is that now B2 is higher above B1 because it's killed less. So let's see if that's kind of what we expect. Yeah, it's actually massively so. Apparently what we changed made it such that now B2 is the total winner and B1 goes completely away. Initially they both start, but then when the immune response, the innate one ramps up, it seems to completely clobber B1 and B2 seems to win. So, this is a simple example where we now have we say, okay, now we have here two different genotypes. Now let's let the adaptive response do something too. I'm gonna, so we can keep track of things. Okay, let's see why the adaptive response. It doesn't seem to be induced, which is the RA and H. So maybe we need to mark RH larger, and maybe H smaller. I'm not sure yet. I can try her. 10. 2. Let's see what this gives us. Oh, okay, now maybe we made it a bit too strong. Okay, it's coming in now at the end here, the adaptive response at the time 10. So maybe if we make it just a little bit stronger. Okay, now this is a bit interesting behavior. Maybe we go on a log scale real quick to see. That's it. Okay, I don't remember my own functions. So let's see what we need to do for optional X scale. Okay, so what we need to do is put another thing into that res object in that list and call it log 10. And then let's see if that works. Okay, now it's on log scale, so we can see a little bit better. So we have the B1 and B2 starting, the innate response comes up real fast. You know, here the blue dashed line. Then the innate seems to be alone strong enough to reduce B1, not B2. So B2 and innate stay up. Then the adaptive comes up. And at some point, the adaptive is strong enough to reduce B2. And of course, once B2 goes down, because the innate response is induced by how much bacteria there are, the innate response will start settling down as well. So that's kind of the dynamic we're getting out of this fairly simple model. You know, could be reasonable for a certain biological system. Of course, here we're just sort of exploring, you know, usually you have a more specific question in mind where you say, well, I know, or I think that this is how the two strains differ. Let me put this in the model and see how the difference in strains will affect the results. So usually this is the way you're going about. You're kind of, here we're just playing around, but usually you have sort of a question where you say, okay, this is what I think will happen. But you can see, you know, it's not necessarily clear that just because we have these killing from the adaptive innate different, qualitatively we might know, yeah, of course, if the strain 2 is less strongly killed by them, then it will be doing better to B2 than compared to B1. But for instance, I couldn't have told you that B1 will be completely removed and B2 stays around. I thought maybe both of them would be hanging around. So, you know, those are the kind of things you can explore. And there might be a regime where that would happen. We could, you know, let's maybe make these not quite so strong. So maybe only half. Let's see what we get there. So remember the other one was 10 to the minus 4. So this is now 5 to the minus 5. So about half instead of a 10-fold difference. So let's see what happens. Yeah, okay, no, B1 is able to hang around for a bit longer, but then eventually drops off too. One thing you might notice here, you know, we're here in a log scale, we're going here to, you know, 10 to the minus 3, 10 to the minus 7. So of course, in some sense, that doesn't make sense. You can't have a fraction of a bacteria hanging around. That's one of the limitations of these differential equation models, because they treat it as a continuous variable. Now, if you have really large numbers, that usually doesn't matter. You know, if you have 10,000 or 11, you know, or 10,001 or 10,000.5, it's basically the same behavior. But if you get to low numbers, you have to be kind of careful. So sometimes what you might want to put in this code here is that, you know, you have sort of a monitoring bit in your code, and the DSAIRM package actually allows you to write that if the bacteria drop below 1, then you call it over. Then you just set them to 0 instead of letting them go to a fraction. If you really have low numbers and start worrying about that, and sometimes in these kind of models where you have a new variant that might emerge, then you actually might have to move to stochastic models, which are different, and they can treat that in more detail. And there are a few stochastic models in the DSAIRM package. So if you're interested in that, or you think that might apply to your setting, you could apply it. Yeah, and so the question, could we consider everything negative, the fraction to 0? Yeah, so that's an approach you could do. You actually hope that it doesn't turn negative, because negative doesn't really make any sense. And then often what happens if something turns negative, your ODE solver will get all confused, and things will just blow up, because now you had like an outflow, but if one variable is negative, it would suddenly became an inflow, and things blow up. So, sort of just a behind the scenes comment here, things like this, which is tolerances. It's called the absolute and relative tolerances. These are two settings of the underlying numerical routine that kind of tells it how careful it has to be when it does its numerical thing. And the trade-off is that the larger the numbers, the faster your code runs, but also the more likely that you might encounter where it takes basically a step that's too big, and then things turn negative. And the same here with that method here. There's certain methods you can choose that make things more or less robust. The trade-off is always, if it's more robust, then it tends to be slower. In this case, I don't care about speed much, because it's a very simple model. So I'm going with very low tolerances and a very robust method. But in other settings, that's something you need to think about. And since we talked about agent-based models before, agent-based models, you always need to take a time step, a finite time step. And since agent-based models are often computationally very expensive, they take long to run, you need to kind of find, okay, what's the biggest time step I can get away with? That still doesn't make time steps that are too big. If you're trying to model, let's say, flu, on the population level or the within host level, time steps of a month make no sense, right? Because everything happens in a month. It starts, it goes away, everything's done. So if you step from a month to a month, a person didn't have it, and a month later they again don't have it, but they had it in between. So there you might need time step of days or maybe hours. Now, on the other hand, if you wanted to model TB, maybe you can get away with time steps of months, because you want the long latent phase. So for those kind of models, it becomes more important to figure out, okay, what exactly, where's the trade-off that I need to make? And often that's trial and error. You try some out, you say, okay, this is not yet good enough. You try something else, and then, computational speed factors in as well. Okay, any suggestions what else we should do with this model? Or, scientific questions, or any way we should extend it and play with it. We could put in more details now. We could make all these other parameters different between the two strains.
Do you know how fast R is at handling like stochastic models? Do you have any idea about that? Is it slow or fast?
It's a bit of a hard question, because most of the time you use a certain package to do it. And there's huge differences. So the one I like and the one I'm using in DSAIRM is called adaptive TAW package. And that has two advantages. One is the actual code underneath is written, I think it was C or Fortran, one of those, so very fast language. And the other one is that it actually uses sort of a smart algorithm that makes approximations when appropriate, which means, you can run a lot of stochastic models pretty quickly, and it makes careful steps when the numbers are low when it's necessary, and then it takes bigger steps when the number are big. So that one, in my opinion, tends to run really fast and works really well. So, we could, since we have this open here, where is the stochastic one? Oh, which one does the stochastic one? Oh, here, stochastic dynamics. So if I run in here, you see I just ran the ODE, but you can also now say stochastic or both. And you could say how many simulations. Another thing where stochastic one gets slower is because now, if you run an ODE model, every time you run it, you get the same answer unless you change your parameters. That's not the case anymore for stochastic models, even for the same parameters, because there's noise in the system. Every time could look slightly different, or sometimes quite a bit different. So to get sort of good estimates for stochastic models, you need to run them a whole bunch and then sort of look at the distribution and report maybe the mean and the spread or things like that. So that's another reason why even if one stochastic model runs as fast as the equivalent ODE model, you have to run the stochastic model 100 times. So that's another thing where stochastic models become slower. But when we run it now, so now you see there's a bunch of stochastic runs and ODE. And I ran it 10 times. Are you wondering why you don't see 10? It actually turns out that a whole bunch of them are sitting up on top here. It just so happens that for those stochastic ones, the infection never took off. And that's another interesting one here, because for the ODE model, it either always takes off or it never takes off. And that comes back to that R0 idea that we talked about before. For stochastic one, there's a probability that it can take off. If your R0 is less than 1, it will never take off. But if it does, it takes off. So in this case, it actually, it reports it to you. It says, 2 simulations produced an outbreak, meaning those 2 here, and all the other ones did not. Now we can make it more likely that something takes off by starting with more virus particles, because then the chance that they all die away before they have a time to replicate is reduced. So now if we run it now, let's see. Okay, now you see 8 of the simulations, it actually took off, all these gray lines. And because the numbers are so high here, it looks very smooth, even though there's jitter. If we make the numbers lower, and then I need to adjust other things. See, now it gets more wiggly. So you see for the stochastic one, you see the jitter, the noise in the system, while the ODE ones is always completely smooth. Okay, so there's a suggestion. How about trying 2 types of adaptive immune response? IL-17 versus gamma. That would be more likely the innate, right? We can do that. Yeah, we can try to stick in 2 different innate responses. So let's do that. Let's put in 2 innate ones. So the scheme should be clear by now. We're just copying innate and calling them 1 and 2. So first, wherever I see the I, I'm going to call it 1 and 2. And then after that, I'm going to visit the parameters. Oops. So now we have to, okay, so I don't forget, let's put it in right here down there.
In line 22, just replace 1 for 2. After, yeah.
Oh, here, yeah. So we have to decide again that max thing, what's the maximum saturation for those? Now, in this case, if we're thinking one of them is IL-17 and the other one might be interferon gamma or something like that, it's quite likely that their maxes are different, right? Because they're even on different scales. So, I would be inclined to say, well, they actually should be different. And the same here for the rate at which they decay, and probably even for the rate at which they grow. So because they're not, before it was 2 different bacteria, but they were, kind of similar potentially, just was a, genetically slightly different. But now if we assume here, these are 2 completely different types of the immune response, then we probably need to let them be very different. So I'm going to do that here. And then, of course, now we also need to have here the, how do I do that? You know what? I think I'm going to change things around. I'm going to undo everything I did. I'm going to just give them a completely different name. So this is now the interferon response, let's say that. And that was the IL whatever response. Just so, we don't get too confused with all the indices. Okay, so there's no, it doesn't matter, right? But whatever is easier to wrap your head around. But now what I what I can do here is no, this stays. So I just use 1 and 2 now for the strains, for the bacteria strains, and otherwise I have completely different ones. So let's go through it. This is right. So this is now the old killing by the whatever I is, IL-10 or something. And this is now by the new one, by the F one, which could be interferon or something. So we have them have their own parameters here. Now we need to potentially change this one here. So, we need to decide what we think these two components do for the adaptive response. We have different options. We can either, again, say it's just the sum of the two. Or we can say, no, we assume it's the IL-10 response that induces the adaptive and not the interferon. Or we could do it the other way around. We can say it's the interferon, but not the IL-10. I don't know what biologically makes the most sense. Maybe I'm just deciding now that it's actually just induced by the interferon response and not by IL-10. So, that we now can have the innate response do something, but it doesn't actually trigger the adaptive, and only the F part of the innate response actually triggers the adaptive one. So we'll see what happens when we do that. Okay, now we need to do it everywhere else, and now especially here, all these parameters we now have. Basically, let me just put them down here. And then also okay, so these are all the new ones, the 2 Ks and this. Now you see what I'm doing here still, I assume they follow the same on and off kinetics here. Now we could change that, of course, as well. We could say, well, that interferon response doesn't grow according to this pattern. It grows according to some other mechanism. Again, if you have a real system, you're putting in what you think is the most realistic in the form you think makes the most sense. And then now we have to, this is starting to get big here. And yeah. You're wondering what that weird notation something equals something is. In R, that's that vector is what's called a named vector. So now I can call them by their names instead of just the position. That's why I have to do this somewhat weird notation. Okay, let's see. I would be very surprised if this runs, but I guess unfortunately I didn't. You know what? I'm gonna save that as something new. And then when I'm giving it to you, I'm going to clean up and revert to the old one. So you will have versions of each. Okay, this one worked. Huh? It worked. Let's see what the plot does. Okay, something happens there. So now we have I and F. They track each other very closely, which is probably because we chose the same value still for each. So apart from something here. So we might want to adjust that now. So let's see. We have RF and F max. So let's say RF grows faster, but has a lower carrying capacity. So let's say RF equals 2, but its max is, what did we have here? Say 10 to the 4. So let's see how this changes things. A bit hard to see, but I guess you can see a little bit that the green one ramps up a bit faster than the blue one. Neither one reaches carrying capacity, or at least the I one doesn't reach carrying capacity. So that doesn't seem to be playing a role here in limiting the growth. Because the growth and decline seem to be kind of in equilibrium below the max. So you can see it's not that complicated yet, but to really understand this model now, we would have to play around a good while to try to dig into it. What I would really do here, if I now want to sort of explore it, I would actually first turn off the adaptive response to just see what the two other components are doing without the adaptive response. And then I might even, turn off one of the two bacteria strains. So, what we already did yesterday, if I wanted to explore this model, I would turn on different components. So I might just do a single bacteria and the two innate responses, or a single bacteria and one of the innate and the adaptive, then a single bacteria, the other innate and the adaptive, and then both bacteria and maybe one or both innate. So I can understand what each component is doing, even if in the end I want them all in there. If you run them all at the same time with different values, there's just so much to explore that it can get easily overwhelming. But if you do it bit by bit, you definitely need to do that for debugging too, because there's likely bugs in there and things go wrong. So you can test each part. If you have the activation rate of the adaptive response 0, it shouldn't come up, right? If it does come up, then you're like, okay, I did something wrong in my code somewhere. So, and then once the code works, for understanding, you want to build bit by bit. And then once you think, okay, I understand this, then you can throw it all in there. So, if you see really big models in the literature, for instance, we're talking TB here, and I mentioned it before, Denise Kirschner has done a lot of TB models. And if you go to her maybe more recent models, some of them have like 40 or 50 equations and a lot of parameters in there. So it's really looks complicated. It is complicated. But the thing is, she's been doing that for so long, and she started with simpler models that, she just keeps putting bits in there. And, because she has all that experience with these kind of models, she can sort of get a handle on what's going on there. If you build your own model from the beginning, I always advise start simple. And then as you get more and more sort of understanding of that system in the model, you put in additional details. Anything else you think we should be doing with this model?
So I was thinking maybe we could try starting out with a wild type population that diversify or acquires mutation. So it would still be adding a second compartment, but it would not starting out with two populations of bacteria, but starting out with the one population kind of like changes over time at the X mutation rate.
Mm-hmm. So we can try that. Now to do that nicely and cleanly, we would need to again have probably a stochastic model where we start with 0 and then one bacteria is produced in 2. Now we can try to approximate it here with this kind of model. And so basically what we could do is, instead of having initial bacteria 2, we start with 0 there, but then we have a low rate here at which when bacteria 1 grows, there's a small amount, mutants that are produced here. So we have, let's say, 1 minus mu, and that might be mu is the mutation rate, which is very small. So most of them will just be growing and producing wild type again as they grow. But a small fraction here will be of the B1 bacteria will mutate and will therefore end up in B2. And then once they're B2 around, they do all that other stuff that they've been doing before. They're doing their growing and decline. So that, if we now run this and we can try it, what we should see is that, we start initially without any B2, and then it will come up. So the only thing that's new here is I've introduced that parameter mu, and making it very small. So it's small. We'll see if that's small enough or not. And leave the rest, see what happens. I guess I didn't change it in here as well. Okay, no, I changed the name. Okay, now we can kind of see that idea, right? So there's B1 initially at, about 100, and B2 is basically not there. And then it's generated at a low rate, and then once it's there, it starts growing itself. So that's a kind of an approximation. Again, if you really wanted to study that process of things being generated, it's probably a stochastic model would be the better one. But people have used ODE models like this and done it exactly in that form, the way I've done it before, to sort of say, okay, we start there and then it's created at a low rate. And then, you can, of course, explore, if you had a lower mutation rate. Well, actually, I don't need to change it here. I just change it when I call it. So, lower mutation rate, meaning it takes longer for them to come in. And so with those models, you can see interesting things. If you, for instance, included a drug now in that model, which one could also do, you might see an interesting effect that sometimes the intermediate treatment is the worst that you can have. And actually, I wonder if one of those that I have in here does that. I don't fully remember if it's in there now. Oh, here, this one, influenza antivirals and drug resistance. This is actually using something along those lines. So where we have a stochastic model, and you have these two here, I call them sensitive and resistant virus. That's kind of like our B1 and B2. And then you introduce a drug. And if you go through it, you will find that out. But what you can see is that, if you have very low drug treatment, then, the sensitive strain wins because it has a fitness advantage in the absence of drug. And if you do a bit of drug, it still has a fitness advantage. Then once you start with more drug, then the resistant will have a fitness advantage and will come up, and the sensitive will go away. Now, when you have a whole lot of drug that you give really early, then there isn't enough time to create a resistant one. So both of them are gone. So you find this interesting thing that sort of the treatment in the middle is sort of the worst when it comes to drug resistance evolution. On the low end, you don't get resistance. Of course, you also don't clear the sensitive strain. So it's not a good one. It's a very high one. You might be able to get rid of both of them. So that's, you can explore that a bit more if you want. And this one uses a stochastic model, which is the one you kind of want to do to do that in more detail. But people have done this sort of approach here with this in a differential equation framework too. And so you can explore it there. And since I mentioned it, one could introduce a drug here, right? What we model doesn't always have to be biological things like the pathogens or the immune response. So, we could have here a minus a D2 times D you know, this would be some killing by some drug. It would be like this. You know, each strain is killed by some drug. Now, of course, I would need to give an equation for D. All right. So I could at the very now this can get tricky because you know, drug treatment is usually every so often, right? And so in these differential equations, to do something that's pulsed, where you say, you know, every day, you basically have to sort of run your simulations for a day, then stop it, then increase the drug, then run it, then stop it, increase the drug, something like that. So that makes the logistics of writing the code potentially a little bit trickier. You know, that can be a potential problem. You know, a very simple way, this is a bit silly, but you know, you could just assume you start with some, you get the treatment on day 0, and then it just decays. So that would be, you know, possibility that is, you know, maybe not the most realistic, but just for illustration right now, it would be an easy one to encode. And now we have so these are the new parameters, the 2 drug ones, and then we have the new drug here, and then the drug is just given. So all we do basically, we start with some level of drug. I don't know what a good number is. Let's see. Might be okay. And let's see if it runs. Keep forgetting to rename it. Okay. Yeah. Okay, so this is if you do anything with ODEs and DSOLV, you'll see that at some point. You know, this is basically a warning message that when you're trying to integrate this underlying thing, something is going wrong and something's blowing up there. Must have to do with the drug thing. So let me just set those to 0 real quick. Maybe it's these killing rates. Oh, what did I call them? Oh, maybe the other way around. Yeah. Okay, so somehow the default killing rates are too high. Let me set them something lower. See what happens there. Still didn't like it. Let's think about the model. Oh, wait, this should be B2 here. That might be a problem. Let's try again. That might have been the problem. Now it's going away. So now you see the drug here in the blue color there, in the dark blue. It behaves like we started some value and just is kind of right now an exponential decline. It's not that realistic that there's an exponential decline over 100 days or so, maybe if it were hours, maybe. But just for illustration, a simple one. And so it looks like the drug isn't doing much just now. I guess maybe after we fix this error, we can turn those killing rates up again. Okay, now we see something, right? So initially the drug is high, and then it suppresses the it suppresses B1, and it also then leads to less B2 coming in. But then as the drug declines, it of course doesn't have that much effect anymore. So then things go back up. So, this is arguably not very realistic way we put the drug in there, but just to illustrate how you could do that. And, you can, of course, give the drug a more realistic one. And, in the drug development world, there's a whole field called pharmacometrics. And with that, there's what's called the pharmacokinetics. That's modeling how the drug behaves. And then the pharmacodynamics is modeling what the drug does to the system. So, you have these models where it's like, okay, you take that drug orally, so it goes into your stomach, but where it needs to act is actually the liver. So you have a little model where it moves from the stomach to the liver. and then, you try to model the concentration at the place where it needs to be. And then you have the other part of the model, which is like, given that's the concentration, what does it do? In this case here, I've just modeled it like this, but there's a lot of different ways that are probably more realistic, the way you could model the impact of the drug. Often you have something like low drug, nothing happens. Then as you ramp it up, the drug is effective. Once you reach a certain level, it sort of saturates. And if you give even more drug, it doesn't actually help more. You might just get more side effects. And so trying to figure out the right dosing is a big field there in the drug development world. So there's definitely a lot of those kind of models going on in that area. Okay, we have a few more minutes. Any other thoughts or questions or comments?